I want you to imagine a sound for a second. Picture the screeching, grinding noise of a really heavy metal overhead garage door that just hasn't seen an ounce of maintenance in like a decade.
Oh, yeah. That is rough.
Right. Or, think about the high-pitched, agonizing squeal of a failing fan motor in the dead of summer. Or just that awful sound of two dry metal gears trying to force their way past each other.
Oh, terrible.
It really is a visceral sound. Because, well, it's the sound of physics just totally winning a battle against our engineering. It is literally the sound of friction tearing solid steel apart.
Yeah, and it sets your teeth on edge because intuitively, even if you aren't a mechanical engineer, that sound means something expensive is being destroyed.
Exactly.
Metal is literally shearing off metal at this microscopic level, creating heat and permanent damage.
And yet, for the most part, our industrial world and just our daily lives, they don't sound like that. Like, things run smoothly.
Usually, yeah.
Right. Heavy machinery slides, massive gears turn under immense loads, and doors open in relative silence. And the reason for that is this completely silent, totally unsung hero. A hero that honestly prevents our world from grinding to a catastrophic halt.
The humble lubricant.
The humble lubricant. And today's deep dive is dedicated entirely to understanding how that invisible magic actually works. We are looking at a single, incredibly dense document provided by you, the listener.
A very dense document.
Super dense. It's a technical data sheet, or a TDS, for a very specific product. It's called Jet-Lube White Lithium Grease with PTFE. It's got this bright, bold orange Jet-Lube logo at the top, and below that is just, well, a formidable wall of numbers.
Acronyms, test results, all of it.
Yeah, intense laboratory test results.
I mean, to the untrained eye, it basically looks like a final exam for an advanced chemistry class.
It really does. But our mission today is to decode this wall of text. We are going to uncover the fascinating science of friction and exactly how this specific, premium, all-purpose white goo actually conquers it.
I love that.
Okay, let's unpack this. Because turning what looks like a super dry, impenetrable list of specs into a story about battling the fundamental forces of nature is, well, it's incredibly exciting to me.
It is a great story, and I think it helps to ground this conversation by understanding what a technical data sheet actually is.
Right.
Because when you buy a consumer product at the hardware store, the label on the front is, it's mostly marketing fluff.
Oh, totally. Like, works great or super strong.
Exactly.
Yeah.
But a TDS is not marketing. It is a rigorous, verifiable promise of physics. It's a legal and scientific document.
Wow. Okay.
Yeah. So we are looking at the exact blueprint, the mathematical proof, really, of how this specific grease promises to step in and keep metal from destroying other metal.
And before we can understand what this grease does out in the world, we need to fundamentally understand what it is on a chemical level, right?
Absolutely.
So looking at the base ingredients listed here, there's a thickener called Lithium 12-hydroxy, and the fluid type is simply listed as petroleum oil. So, trying to visualize this, is grease basically like a microscopic sponge holding soapy water?
A sponge.
Yeah, like the thickener, this Lithium 12-hydroxy is the physical sponge, like the structure, and the petroleum oil is the fluid trapped inside that actually does the lubricating work when, pressure is applied.
What's fascinating here is that analogy hits the nail on the head regarding the underlying mechanism.
Oh, really? Awesome.
Yeah, because oil on its own is a fantastic lubricant, right? But if you put liquid oil on an overhead garage door track, well, gravity's going to pull it right off.
It just drips onto the floor.
Drifts right off. So chemists use a thickener, in this case, lithium 12-hydroxysterate, which is technically a type of metallic soap.
Wait, soap?
Yeah, a metallic soap.
Right.
And they use it to create a microscopic three-dimensional fibrous network, a sponge.
Okay.
This sponge traps the petroleum oil. So when two gears mesh together, the mechanical pressure physically squeezes the sponge, forcing the oil out to lubricate the metal.
Oh.
And then when the gears move apart, the pressure is gone, the sponge actually reabsorbs the oil.
That is brilliant. It literally holds the oil in place until the exact millisecond it's needed.
Exactly.
Okay, looking further at its physical state, it lists an NLGI grade 2 and something called a penetration score of 265 to 295 at 77 degrees Fahrenheit.
Yes.
I have to ask, is this penetration number just a really highly scientific way of saying this stuff? Has the consistency of smooth peanut butter at room temperature.
You've pretty much captured the essence of it, yeah.
Nice.
The NLGI, that's the National Lubricating Grease Institute. They grade grease based on how stiff it is.
Uh-huh.
A grade 2 is your most common automotive and industrial consistency.
Gotcha.
And the penetration test itself is incredibly literal. In the lab, they take a standard weighted metal cone, and they basically drop it into a cup of the grease at exactly 77 degrees Fahrenheit.
So they just let it sink.
They just let it sink, and they measure how many tenths of a millimeter that cone sinks into the surface.
So here it sank between 265 and 295 tenths of a millimeter. That proves the sponge is exactly the right stiffness.
Right.
Like, not so hard that it acts like a brick and not so soft that it flows like syrup.
Exactly. It's the Goldilocks zone for general use.
Now, the document also claims this grease is very adhesive, forming a long-lasting protective film that will not run or wash away.
Yeah, that's a big claim.
Right. And I see it has a specific gravity of 0.95 and a density of 7.80 pounds per gallon. Does that sheer physical weight and density make it adhesive? Like, is it just heavy enough to stay put?
Well, that's a very common assumption, but the specific gravity actually just tells us it's slightly lighter than water.
Oh.
Yeah, meaning if you dropped a glob of it in a bucket, it would just float.
Okay, so it's not the weight.
No. The actual stickiness, the reason it's so adhesive and clings to high-speed parts without flying off, that actually comes down to the molecular structure of that lithium soap thickener we talked about.
So it's a chemical thing, not physical weight.
Exactly that. The soap molecules are polar.
Polar, like a magnet.
Basically. They carry a slight electrical charge that makes them inherently want to grab onto a metal surface. It creates a literal chemical cling.
Wow.
So even if a fan motor spins up to thousands of RPMs, that polar attraction fights the centrifugal force that's trying to fling the grease into the air.
Okay, so we have our baseline. We have a perfectly engineered microscopic lithium sponge clinging electrically to the metal, and it's holding a reservoir of petroleum oil.
A perfect little system.
But machinery gets incredibly hot, and, it gets exposed to the elements. So our soap sponge is going to be put through absolute hell.
Oh, without a doubt. That transition from a static physical state to a hostile thermal environment, that is where the chemistry really gets pushed to its absolute limits.
Yeah, because the document lists the temperature ratings, and the service rating spans from a freezing 0 degrees Fahrenheit all the way up to a scorching 370 degrees Fahrenheit.
Those are massive temperature swings for any chemical compound to endure without just totally breaking down.
Here's where it gets really interesting, because I'm looking at the math here and I need to push back a little.
Sure.
The document proudly states it's rated for service up to 370 degrees Fahrenheit. But just a few lines above that, it lists a dropping point of 390 degrees.
Right.
Is the dropping point the literal temperature where our carefully engineered chemical sponge finally just gives up, melts, and drops all its oil?
You've hit on a crucial piece of engineering safety there. Yes, the dropping point is the exact temperature where the grease transitions from a semi-solid sponge back into a basically useless liquid.
Oh, man.
At 390 degrees, the three-dimensional lithium soap structure simply collapses. It just melts, and the trapped oil drops right out.
Meaning, if you operate a machine at 390 degrees, your grease turns into hot liquid oil, runs away down the drain, and your machine is just destroyed.
Completely destroyed, which is why the service rating stops at 370 degrees. The manufacturer is giving you a strict 20-degree safety buffer. It's a scientific promise that if you keep your machinery at 370 degrees or below, the structural integrity of that grease will hold.
It will not melt.
It will not melt.
Yeah.
And it's also worth noting the other thermal defenses listed here. It has a flash point of greater than 430 degrees Fahrenheit and an autoignition point of greater than 500 degrees.
Okay, so it won't even produce flammable vapors until 430 degrees, and it won't spontaneously burst into flames until over 500 degrees.
Right.
That is some serious heat resistance, but surviving heat isn't the only environmental hazard, right? You also have to survive the chemical environment, like oxygen and moisture.
Oh, for sure. And that brings us to the additive type section. Basically, the alphabet soup of chemistry mixed into the oil.
Right, I'm looking at it. It says organic EP, AEW, R&O, PTFE.
Let's focus on the R&O first. That stands for rust and oxidation inhibitors. See, bare metal inherently wants to rust when exposed to moisture. And petroleum oil naturally wants to oxidize and turn into this thick, useless sludge when exposed to air and heat.
Sounds messy.
It is. So the R&O additives, they act as chemical bodyguards against that.
And we know they work because the document gives us the proof. The oxidation resistance test shows less than a 5 psi drop over 100 hours of testing under pressure.
Exactly.
It basically just ignores oxygen. And then there's the copper strip corrosion test, where it scores a perfect 1A. What is that?
The test is fascinating. They take a freshly polished strip of copper, which is, highly reactive and tarnishes incredibly easily.
Right, like an old penny.
Exactly. They submerge it in the grease and they bake it in an oven. A 1A score means when they pull that copper out, it is still perfectly shiny.
No way.
Yeah. It proves the lubricant won't chemically eat away at the very metal it's supposed to protect, even under extreme heat.
That is incredible. But wait, I'm looking back at that additive list. Organic, EP, AW, RNO, PTFE. We skipped a letter in that soup, or, well, an acronym.
We did.
And it's actually in the literal title of the product, Jet-Lube White Lithium Grease with PTFE. What is PTFE and what is it doing in our microscopic sponge?
PTFE is polytetrafluoroethylene.
Say that 3 times fast.
I know, right? But most people actually know it by its brand name, Teflon.
Oh, wow. Teflon. So they put Teflon in the grease.
They do. And the mechanism is brilliant. Remember how the pressure of the gears squeezes the liquid oil out of the sponge?
Yeah.
Well, if the pressure gets too extreme or the oil gets temporarily pushed away, you need a backup plan. The PTFE acts as microscopic, solid, ultra-slippery flakes suspended throughout the whole mixture.
Oh, I get it. Like throwing microscopic slippery marbles into the mix.
Exactly that. It provides a secondary layer of solid lubrication. Even if the liquid oil boundary fails for a split second, those Teflon particles are still sitting on the metal surface.
So the gears can still slide past each other without catching.
Right. It's basically a physical insurance policy against friction.
Okay, so we've seen how this grease survives heat, resists oxidation, and brings Teflon marbles as backup.
Yeah. But surviving heat and water is only half the battle. If we move from temperature to physical pressure, we enter a whole new level of stress. Like, the true test of a heavy-duty lubricant is surviving immense, crushing physical force.
Oh, absolutely. This is the part that truly separates your standard, everyday household lubricants from heavy-duty industrial ones.
And the TDS has a whole section dedicated to this. These are the ASTM tests, specifically the 4-ball tests.
Right.
They list a weld point of 200 kilogram F, a load wear index of 25, and a wear scar diameter of 0.7 millimeters.
That's very specific numbers.
I'm looking at this weld point and 4-ball test terminology, and honestly, I'm just picturing some medieval torture device where they grind metal balls together until they literally melt into one piece. Am I totally off base?
Well, if we connect this to the bigger picture, you are actually picturing the end result perfectly.
Wait, really?
Yeah. The machine they use to do it is called a 4-ball extreme pressure tester, and it is brutal.
Tell me.
So they lock 3 steel balls tightly together in a triangle formation inside a small cup.
They fill that cup with our Jet-Lube white lithium grease. Then they take a 4th steel ball, press it down into the center of the triangle, and just spin it at thousands of RPMs.
Oh, man. So you have one ball spinning furiously against 3 stationary balls with only this microscopic layer of grease keeping them from destroying each other.
Exactly. And then they start adding weight.
Of course they do.
They push that 4th spinning ball down harder and harder. As the physical pressure increases, the oil film desperately tries to squeeze out of the way. The friction goes way up, and localized heat spikes dramatically.
And the document says the weld point is 200 kilograms. That's kilograms force, right?
Yes.
I did the math on that, and that's roughly 440 pounds of pressure on a pinpoint.
It's massive. It means the machine had to apply 440 pounds of force onto a microscopic point before the grease film completely failed.
Wow.
And when it fails, the raw metal finally touches, the heat flashes, and the 4 steel balls instantly weld together into a single, solid chunk of metal.
That is absolutely wild to think about.
Yeah.
But how does it survive up to that point? We talked about the Teflon, but the additive list also mentioned EP and AW, extreme pressure, and anti-wear additive.
Right.
Are they just providing like a thicker fluid cushion?
Actually, it goes much deeper than just a fluid cushion.
Right.
This is where the chemistry does something almost magical.
Okay, I'm listening.
When the pressure spikes and the heat flashes right at that microscopic point of contact, those EP and ADW chemicals react to the extreme temperature. They instantly bond with the steel to form a slippery, glass-like chemical crust over the metal.
Oh, wow. Like a protective scab forming instantly over a wound.
That's a really great way to think about it. The spinning machine ends up grinding away this sacrificial chemical crust instead of grinding away the actual steel.
That's crazy.
And once that crust wears off, the heat spikes again, and a new layer instantly forms from the surrounding grease.
So the chemistry literally throws itself in front of the friction to save the steel.
Yeah.
And the document proves this with the wear scar diameter of 0.7 millimeters. Like, it proves that even under grueling, continuous pressure, those additives keep the actual physical damage to the metal to less than a single millimeter.
Exactly. And, we shouldn't forget the foundation supporting all of this, which is the base oil viscosity.
It's listed as 100 to 160 centistokes at 40 degrees.
Right. That tells us the petroleum oil trapped inside our sponge is a heavier, thicker fluid. It's designed to provide a really robust hydraulic cushion to carry the heavy load before those chemical crusts even need to form.
Okay, so we've seen this invincible white paste survive the ultimate laboratory torture tests. We've seen it bake in ovens, resist oxidation, and form sacrificial glass layers to withstand, like, metal welding force.
Did it through a lot.
It really has. But where does it actually end up out in the world? Because the TDS lists a huge variety of applications, and the range is honestly kind of mind-boggling.
The sheer versatility is definitely a major selling point for engineers.
I mean, they break it down into categories. For industrial, they list heavy machinery, tools, overhead garage door channels, fan motors, slides, and gears.
Standard heavy-duty stuff.
Right. For marine, it's cables, couplings, hitches, and winches. For automotive, we're talking hinges, latches, springs, coils, and even electric antennas.
Sure.
And residential, it's door channels, slides, and locks. But as I'm looking down the list, wait, I see a very specific, highly regulated badge here.
The food service compliance.
Yes. It says it has NSF Reg, hashtag 137549, and that it meets 1998 USDA H2 guidelines for use in federally inspected meat and poultry plants.
Quite the mouthful.
And it's also authorized for use by Agriculture Canada. So what does this all mean? Why is an extreme pressure Teflon-infused automotive grease going anywhere near our food supply?
Well, this raises an important question about the reality of modern food production.
How so?
We tend to think of food processing plants as these pristine, quiet, stainless steel kitchens. But in reality, they are heavy, brutal industrial environments.
Well, I guess that makes sense.
And think about a massive conveyor belt system moving thousands of pounds of poultry an hour. Those belts have massive drive chains, huge gearboxes, and heavy bearings taking immense loads.
And they operate in highly humid, constant washdown environments where, rust is a never-ending threat.
Exactly. They have the exact same friction, heat, and wear problems as an automotive assembly line or a marine dock.
So they need the heavy-duty stuff.
They desperately need that 200 kilograms force protection and the Teflon backup. But because it's a food plant, you can't just bring in any toxic, foul-smelling heavy metal grease off the street.
Hence the alphabet soup of government agencies, the NSF, the USDA, Agriculture Canada.
Right. The bureaucratic rigor required here is immense. Getting an NSF H2 registration means independent toxicologists have reviewed the exact chemical formula.
Wow, every ingredient.
Every single additive, the thickener, the base oil, they have to certify that while it is an industrial chemical, it does not contain specific heavy metals, known carcinogens, or extremely toxic substances that would make it a hazard just by existing in the same building as food.
But the document is incredibly strict about that H2 designation. It specifically says, in all caps, non-contact areas only.
That is the absolute line in the sand.
Okay.
See, an H1 designation would be for a lubricant where incidental food contact might happen. But H2 means it is safe to use in the facility, say, on an overhead crane track or a gear hidden deep inside a sealed motor housing. But it must never, ever touch the actual food.
That makes perfect sense.
Achieving a balance of hardcore industrial strength performance while still meeting those strict health and safety compliance rules, it is a very difficult tightrope for chemical engineers to walk.
It's absolutely fascinating. I mean, we started our journey today by looking at this bright orange Jet-Lube logo and what looked like a painfully dry wall of specifications.
These numbers on a page.
Right. We had penetration numbers, flash points, and kilograms of force. And by unpacking it, we've revealed this amazing narrative. Like, we are looking at a highly engineered, heat-resistant, pressure-defying chemical sponge.
Beautifully said.
It's basically a microscopic fortress of petroleum oil, lithium soap, and Teflon marbles that chemically sacrifices itself to keep our world moving smoothly.
It really is a perfect example of how much incredibly complex, invisible science goes into the most unglamorous, overlooked parts of our infrastructure. Grease isn't just sludge you wipe off your hands. It is a highly tuned chemical instrument.
It really is. And I want to leave you, the listener, with this final thought to mull over. Right now, as you listen to this, take a second and think about the sheer amount of mechanical friction happening all around you.
It's everywhere.
Everywhere. Every door hinge in your house, every spinning fan motor in your computer or your air conditioner, the heavy track of your garage door.
Yeah.
There is a hidden microscopic battle going on every single second to keep those metal surfaces from destroying each other. It's a violent, high-heat battle fought silently by precisely engineered invisible layers of white grease and sacrificial chemicals taking the hit so the metal doesn't have to.
Spot on.
So the next time you push a heavy door and it swings open completely silently, ask yourself, what other invisible engineering marvels are you taking for granted in your daily life?